Hello again. In the previous uh, lecture, we summarized the reasons why we should learn statistics into three key reasons. Number one, variability. Number two, uncertainty. And number three, subjectivity. Now we need to move to another important question, which is what is statistics? What is this science is all about? Why we learn statistics? We'll give you a general idea, but now we need to know how the subject or the science of statistics will help us addressing the why. And in order to know that, we need to know what is statistics. Well, if you go into different definitions of statistics, if you Google that, you're going to find many definitions. And as you can see here, here is one definition. Statistics is the science of collecting, analyzing, presenting, and interpreting data, as well as of making decisions based on such analyses. But that is a very general definition. More specific definition will look something like this one. The American Heritage Dictionary, for example, would define statistics as the mathematics of the collection, organizing, and the interpretation of numerical data, especially the analysis of population characteristics by inference from sampling. And you can see that there are common terms used of this definition and the previous definition. But the key term here is mathematics. And anytime you use the term mathematics in any definition, obviously people will get a bit turned off, especially students and people who have math anxiety. If you look at another definition, the Webster Dictionary definition, it's the branch of mathematics. And you can see again that mathematics is coming up as a critical term of the definition of statistics, a branch of mathematics dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. Well, let me make a very important point here. Mathematics is essential for statistics. Without mathematics, statistics as a science would not have been developed. So we need to take that. However, what we are learning in statistics in this course is really applied statistics. Meaning, yes, statistics based on mathematics, but we are not going to deal much with the mathematics. We're going to touch and go on some of the mathematical principles of statistics. But are you going to derive equations, for example, or deal with calculus or even algebra? The answer is no. Indeed, what I mentioned in the first introductory lecture of the syllabus, all I'm asking you to do is to be able to add, subtract, multiply, divide, square root. And all of this using a manual or a scientific calculator, or even a basic simple calculator that can perform these arithmetic functions. So that is really the good news. That makes us focus on the true meaning of statistics and the meaning of what statistics is all about. And as I said in the first lecture, if we have a lot of data, we will use some kind of software, including a simple Excel data analysis, and I will go over that later on, where it will help us doing what a calculator does, but for a large amount of data. So all of these good news, and since we have all this good news, and since we don't have to deal with mathematics directly, let us go into a much more general definition. This definition, the reason I like it is that it covers 10 of the most common terminologies in statistics. These are terms that you must get very familiar with in order to proceed with this course. Why? Because we're going to use these terms a lot throughout the whole course. The definition is the science and art of reading, describing, and manipulating data, which represents variables so that practical observations about a population can be made from a sample drawn from the population, and guidelines can be established to allow making conclusions with high levels of precision and accuracy about a certain process or a given system. That's a very long definition, but it covers all the most common 10 terminologies that we will need in statistics. You can see here the underlying terminologies. First, the word science, we need to understand that, versus the word art, how science compare to art. Because statistics comes in the middle between science and art, as we will find out very shortly. The second term, the term data. What is data? If I ask you today to define data for me, how are you going to define the term data? And I know this is a term that you hear about it all the time. The fourth term will be variables. What is variables? The next term, a population. What is a population? The next term is a sample. What is a sample? And the next term is precision versus accuracy. Are these two terms alike to describe the same thing, or there is a big difference between precision and accuracy? The next term is process versus system. Are these two terms alike, process and system, or there is a fundamental difference between these two terms? So you need to pay attention to these 10 common terminologies because they are used in statistics, and sometimes people confuse these terms and they misdefine them. So our job here first is to define these terms one by one. The first two terms that we saw in the definition is the science and art. And you can read a little bit more on the chapter about the difference between the two. But science is normally based on a theory developed, mathematical theory or physical theory of some form. And based on the theory, you can either test the theory or develop your own theory to reach some conclusions. Art, on the other hand, is a subjective term. Being artistic, it is an individual talent. Yes, you can learn a lot about art in many sources. However, the term art implies often subjectivity. So you can think of the science versus art in an alternative way. You can think of them as objective versus subjective. When we say objective, then we need data. We need reliable information to make conclusions. When we say subjective, then we need our artistic talent, the art, to be able to interpret the outcomes. And sometimes art and science must work together. There are a lot of phenomena that we can collect a lot of data and information about them, but unless we have our own artistic or judgmental talent, we will not be able to interpret the outcomes. To explain to you the difference between science and art in the context of statistics, let me give you a very, very simple example that you see just about every day. You wake up in the morning and you look at the mirror to see how you look. Perhaps you have an interview Perhaps it's a very important day that you need to be well dressed before you leave. What you see in the mirror is what we call statistics. Why is that? Because, first of all, what you have in the mirror is based on a reflection. So there is a science into being able to see your face in the mirror. Also, what you see in the mirror is how you look, how your hair look, the dimensions, the fitting of clothing, the color match. All of these are descriptions. That is what we're going to call later descriptive statistics. And we're going to describe you using data, using analytical information. And that will be the end of statistics, is what you see in the mirror, what you read in the data, what you see in the output of the analysis, the statistical analysis, that is, which is the science aspect. And that's very easy. You will see how automated the scientific aspects of statistics using a simple software or even using your calculator. But it remains to see a very important issue here is after you look at your face in the mirror, after you can see the description of how you look, then the question that you always ask yourself, how do I look? Now, how do I look is often a subjective aspect. You may be happy with what you look. You may be happy with the outcome of the mirror image. Somebody else may actually be standing side by you and looking at your face or your dress and say, wait a minute, I don't like that. So that's a different interpretation. So your judgment of how you look is the artistic aspect, and it's often subjective. Nobody look at the mirror and say, well, my tie is about 8 inch long, my eyes is about half an inch diameter. Nobody does that. What you do when you look at the mirror, you're actually describing what you see in a collective fashion, and that is the artistic aspect of statistics. So once again, there is a science and there is an art. And here is the good news. In statistics, the science is only 20 to 30% of the task that you will be performing. Why is that? Because everything is automated. Either using the calculator, using the some software, everything is automated. Once you learn it, you can just repeat what you do. It's an automated, repeated work. Yes, it is based on mathematical concepts, but you don't have to deal with that as you mentioned earlier. So that is 20 to 30% of the effort you'll be making. But 70 to 80% of the effort will be in the artistic side, on the subjective side. Now that I've done statistical analysis, what can I do with it? What's my interpretation of how I look? Should, for example, I need to change my hairstyle? Should I change my tie or my dress because it doesn't match the rest of my clothing? And so on. These are all subjective, and these amounts to about 80% or 70 to 80%. And I will show you that by examples later on. So now we know briefly the difference between science and art, and again you can read in the book more about the difference between the two. Let's continue the definition. The science and art of reading, describing, and manipulating data. So we now have a third term that we must describe, which is describing. Now, describing data can be done subjectively if it's a simple data set or a few numbers, or it can be done analytically, as we will show you. In fact, the first or the next two chapters are all about what we call descriptive statistics. That is where we're going to learn about how to describe data. We're going to describe data numerically by numbers, and we're going to describe data graphically by pictures. The next term is data. So the science and art of reading, describing, and manipulating data. What is data? If I ask you today to define the meaning of data, what would you tell me? Think about that for a second. In fact, you may want to pause the video and try to answer the question, what is the meaning of data? When somebody mentioned the term data around me, which is always used, often used, what would be my understanding of the term data? What do they mean by data? Well, in order to understand the meaning of data, first of all, data originated from the term datum, which is a Greek term, and it really means reliable or factual information. So data is equivalent to information. Keep that in mind. Data is equivalent to information. What's information means? It means something that informs me about something. Let me give you an example. Suppose I have a bunch of numbers. So let's start out with numbers first. I look at the bunch of numbers that you see in this slides. 100, 140, 213, 230, and so on. What are these numbers? Are these data? The answer immediately is no. These are not data. These are just digits. These are just numbers. Why? Because they don't inform me with anything. What is the information I can get out of that? So now you see why the definition of data is factual information. I have to have information obtained. If it's just digits or numbers as we see here, these are not information. These are not data. These are basically called numbers. So numbers is really one form of output or input, but it's not data. Why? Because there is no information coming from pure digits or pure numbers, as you can see here. So now, if I tell you that the same numbers I just showed you represent human weight. Aha. Now we see something now. Now I can look back at the same numbers I was looking at a minute ago and couldn't understand what they mean. And now I can develop some meaning here, right? A 100, that's about 100 pounds weight. That is a lightweight. A 180 or 280, that's a heavyweight. Perhaps a 160 is a middleweight. So now I am getting information from these numbers. So they are no longer numbers. Why? Because they look like digits, they look like numbers, but they mean something to us, which is human weight. That is what makes numbers data. We often do calculations in a lot of things in different courses, and we fail to define the numbers we're producing. You divide 8 by 2, so you get 4. What is 4? What is 8? What is 2? These are all numbers. But only when you say, well, I have $8, I'm dividing it by 2 people, so each one will get $4. Now we're talking data. Because of that, you must define any numbers you produce by what they mean and also by the units. That is what make numbers data. And now I can divide my data. They are now data, they are not numbers anymore, into lower values and the higher values. I can go in an ascending order, and that will make sense to me. I can look at this data set here and say, well, the lowest weight was 100 pounds, the highest weight was 300 pounds. And I can go on and on describing this small set of data in many different ways. For example, I can say we have 5 people that are 160 pounds or less. You follow me? I can see that some people have heavy weight, 200 to 300 pounds. These are all information that we were not able to obtain when those were just digits or numbers. Now that we can define that they are actually human weight, now that we can define that they are in pounds, then we can easily make some sense out of them. So what is data now? Data are numbers that make sense. Data could be numbers that provide information. Now, do data always numbers? The answer is no. Any type of information that lead to added knowledge are called data. So if somebody would come to me and say, well, the majority of students in campus are 20 years of age or more. He didn't give me any data about the students' ages. He's giving me a sentence or something that he believes it's a fact. So to me, that would be data. If you are investigating 10 people and 4 of them have some kind of anxiety, math anxiety, or some kind of depression, then by virtue of you saying, well, out of the 10 people, we have 4 people that have depression, that is in essence is data. Why? Because we add in information. Okay? The only problem with stopping here is a lot of data could be massive, immense. This very simple ladder that you see here is taking us from numbers, we already know what our numbers are, to data after we define the numbers into some kind of parameter, such as human weight, define the units. But here I'm giving you a few observations. What if these are 200 different data? What if they are 1,000? What if they are 1,000,000? Aha, that would be very difficult to analyze. It would be difficult, for example, to tell what percent of the people have a weight less than 160 pounds. Why? Because I have 2,000 numbers I have. I cannot go over all this data and count how many people that have less than 160 pounds or more than 200 pounds and all of that. So we need to be able to analyze the data. More importantly, who is going to read a massive amount of data? So we need to be able to summarize the data into few parameters or few statistics, such as all of us know what is an average or mean value is. When you calculate the mean or the average of this data set, we are talking about a statistic. When we calculate the minimum value and the maximum value and the range, we are talking about statistics. And notice this, 1, 2, 3, 4, only 4 statistics, only 4 values were able to describe this large amount of data, whether it is 20 observations or 1,000,000 observations, you will always come up with 4 or 5. In fact, we have 5 basic statistics that describe any set of data, no matter how big this data is. So please pay attention to this ladder here. You start out with numbers, which is a raw information. It has no meaning. In fact, it does not inform us with anything. You saw that. Then if we define the numbers, they will become data, which will make sense, like human weight, for example. And then if the data is massive and we need to minimize the massive amount of data down to few useful information, then we will have to use statistics. And that is another reason why we need to use statistics. Let's continue the definition. The science and art of reading, describing, and manipulating data which represent variables. Now, this is really a key issue here, variables. I told you in the previous lecture that statistics is the science of dealing with variability. I also told you that you will hardly find any constant parameter in the world. Everything in the world is variable. Even the ceramic tiles that you buy in a box, which is supposed to be perfectly alike, otherwise you will have a mismatch. If you look at those ceramic tiles, you're going to find them microscopically under a microscope or even magnifying glasses that they are indeed different. They may be different with a minute amount, small amount, but they're still different. Why? Because they were made by human. Human is variable, and if human is variable, then anything a human makes is also variable. Take it from me. That is an absolute fact. What is the opposite to variables? Constants. Well, you are not going to deal with too many constant parameters. In fact, you will hardly deal with any constant parameters. You can pause this video and ask yourself, what is constant in life? What do we see that's constant? What do we see that we see the same thing of it every day? And you will not find any. Some people, for example, think that death is one constant in life. Well, it's true because it's inevitable. All of us will die. But it is not true because when we're going to die is a variable. People will die 5 years from now, people will die 10 years from now. Nobody knows when he or she will die. So as a result, death is a variable, although it sounds like a constant. It's an absolute fact, but it is a variable. So we need to understand the difference between constants and variables, and many examples throughout this course will show us the difference very clearly. You notice here there are some working problems, and these are in the book. There are other problems at the end of the chapter. You need to review these because they apply to what we just mentioned. So variables versus constants. Well, you need to keep in mind that variability can either be inherent or it can be induced. The reason each one of us look different is because God made us that way. We call this inherent variability. But if somebody is doing something in his face, or somebody is doing some kind of Botox or change in how they look, that will be an induced variability. So you need to understand the first that variability can be inherent or it can be induced. Okay? You also need to know that variability can be good or bad. It's really great that each one of us look different. It is really great that we have different talents, different qualifications, different backgrounds. That's, by the way, what makes our country, the USA, is the greatest country in the world. Diversity. And diversity means people coming from all sorts of origins coming together to help this country becoming the greatest country in the world. That's something that doesn't happen anywhere else. So that is a good variability. The fact that we are variable, the fact that we are diverse is really fantastic because this is what I call synergy. Can you imagine you marry someone who is identical to you? Well, guess what? That will be 1 plus 1 equal 1. And you do not need to marry in this case. Now, if you marry somebody who's different, what does that mean? It means good things in you, maybe bad things on the partner or the other way around, so you guys can help each other. So the very end of that would be both of you will reach a level that is good for both of you. We call this synergy. That is not even two, that is more than two. And that's really what synergy means. Synergy means having much more than the numerical sum. 1 plus 1 is 2, but 1 plus 1 in a marriage life is 10, is 20. in terms of synergy. You have a team of people, each one of them is qualified in some areas, but when they get together, they come up with an idea or ideas that cannot be based on just adding up their ideas, but rather a synergy idea, meaning an idea that's better than what each one of the team will have. Variability can also be negative or bad. Imagine you buying ceramic tiles like these. You would expect those ceramic tiles to be identical. That's just by virtue of the fact that they have to match. And if these ceramic tiles are different in dimensions, then we have an issue and you may return the whole package. Similarly, in many situations, people that produce any product like to have this product consistent. Yes, there will be some variability because variability is inevitable, as I told you before. But you go to McDonald's every day, you order a Big Mac, you would like to see it's the same Big Mac that you had the night before and it is not a different sandwich, for example. So if you're providing a service, if you're producing a product, you would like variability to be minimal. That is because a change in what you produce, a change in your surface will imply negative variability. That is the negative aspect of variability. We can also divide variability or variables in terms of continuous variables or discrete variables. As you will see in the book, a continuous variable is an integer. If you say 20, 20 and a half, 20.6, 21, 21.5, 30, we call this the continuous variable. Human age is a continuous variable. You could be 15 years old, 15 and a half, 16, any number. Your grades in a test is a continuous variable. You could have 60, 65, 75 and a half, 80.2. This is continuity, as you can see here. Discrete variables, on the other hand, describe discrete values. What that means? It means it's a stop and go type variables. It's either or. For example, the number of students in a class. This number can be 20, 25 students, but it cannot be 25 and a half. Can you see what I'm saying? The number of accidents on the job. It could be 1 accident per day, 2 accidents, or 3 accidents. They cannot be 3.6 accidents. The number of defects, the number of rejects. All of these are discrete variables, and you can read more about it in the book. Another way to describe variables is quantitative versus qualitative. A quantitative variable is numerical. Your age is a quantitative variable. Your grade in a test is a quantitative variable. Now, how about qualitative? Well, qualitative is your name. Your name is a qualitative variable because it's only an ID. Your name does not make you twice as much as someone else. It's just a name. People name, people identity, ethnic background, race, all of these are qualitative variables. Can we put numbers? Can we make qualitative quantitative? Of course. When you go to the hospital sometimes and they ask you on a scale from 0 to 10, what is your pain level? How painful is your symptoms? Wait a minute. I can only say that I'm very sick, or I feel moderate, or I'm okay. In such a case, I don't have to go to the hospital. But the reason they give you numbers is to scale your pain. It is qualitative variable in nature, but as soon as you assign a number, it gives them some idea about the magnitude of this qualitative variable. So if you put on a scale from 0 to 10, the number 10 or 9, which has no units, That gives the indication that you are in a true pain. When you put 3 or 2, that means your pain is not as much. When you put 5 or 6, that means your pain is an average pain, and so on. That is how you convert qualitative variables into quantitative variables. Why this is important? Because there is no way that we can analyze qualitative variables statistically without converting it into some quantitative indexes. This we see a lot in social science. This we see a lot in psychology research, and it's very important that you understand that. Continue with the definition. The science and art of reading, describing, and manipulating data which represent variables so that the practical observation about a population can be made from a sample drawn from the population. So here we have two new terms, population and sample. Now, in chapter 5 and 6, we will talk a great deal about population and sample under the subject called inferential statistics. And the idea here, you have a population that you cannot access in full. So as a result, you have to take small sample. So population indicates a large entity. A sample indicates a small, a tiny group of people, for example, selected from an area like Manhattan in New York City. So that is a small sample from a large population. That is the meaning of a population and a sample. If you look at here, you're going to see that there is a very important difference between a population and sample. This is a larger population of eggs. This could be 1,000,000 eggs. But what we take in here are few eggs out of these or out of this population. Here we have a lot of people from which we take in just a small sample of people. Now, how we select that sample is a whole subject we will cover under inferential statistics. What information that should be accessible from the population is another issue we're going to discuss under inferential statistics. Can we use the sample information to reveal important information about the population? Because a sample per se is something we're going to use and throw away. We're going to be surveying 5, 6 people, and that's the end of it. But why we are surveying or questioning those 5, 6 people is because we need to know about their population. So the eyes should always be on the population. So can you imagine during the election, for example, when you hear about projection of election results, and people would say, well, this candidate have 55% of the votes, and the other candidate have only 45% of the votes. How did they come up with that? Well, obviously, they did not ask the entire population of registered voters. In fact, most of these polls that you see on TV or you read about in the newspaper, they only take a small sample of 15, 1,600 people. So that's a small sample taken from a very large population. How in the world, using this small sample, you can project what the entire population opinion will be or who they're going to vote for? That is a real challenge. And the statistics can overcome this challenge, and you actually going to learn about that in this course very clearly. And you're going to find that the scientific aspect of it is simple and easy, but the judgmental and the art aspect is really where the essence of the analysis will be. Population versus sample. When we talk about population versus sample, that leads us automatically to talking about statistic and parameter. Look, guys, anything that describe a population, we will call it a parameter. Anything that will describe a sample, we will call statistics. To give an example, the average of a population is going to be called parameter. The average of a small sample, even from that population, is going to be called statistic. And in your book chapter, you can see many examples of statistics versus parameters. In the current assignments you have to distinguish between statistics and parameters, just like you have to distinguish in the same assignment between populations and samples. So you need to pay attention to this issue. This slide here basically summarizes perhaps the entire course of statistics, not just this course, any course. You start out with the population, large population, inaccessible. You cannot access every person in a population. But you want to analyze the population. For example, you want to analyze the age of people in the population. You want to analyze whether the majority of the population are male or female. You want to analyze the income of people in this population. But not every person in this large population is accessible. So as a result, you're going to have to take a sample. But the issue here, how we're going to take a sample? The issue also, how big is this sample that we take from the population? All of this will be addressed under inferential statistics in chapter 5 and on, as I mentioned before. Now, assuming we picked the right sample, now we're going to have to describe the sample. This is what we call descriptive statistics. And chapter 2 and 3 are devoted for descriptive statistics because we must learn how to describe a sample first. Now, description of a sample means producing statistics. I just told you a minute ago. Any measure of a sample is called sample statistics, called statistics. We're going to use the sample statistics now to estimate population. Estimate population what? Estimate population parameters. So the question becomes, can the mean or the average of a sample estimate the mean or the average of a population? That is what we call inferential statistics. And we're going to explain ways to do that. And trust me, the calculation aspect is very simple. And again, it is your judgment of the outputs that will make a difference. You follow me? So we just mentioned descriptive statistics and we mentioned inferential statistics, which are key chapters in this course. Between descriptive statistics and the inferential statistics, we're going to be talking about an intermediate subject called probability. And probability by itself is an independent subject, but it will give you a good idea about how we bridge from describing a sample to estimating population information. Continue the definition. The science and art of reading, describing, and manipulating data which represent variables so that practical observations about a population can be made from a sample. We already learned about all these underlined terms drawn from the population, and guidelines can be established to allow making precise and accurate conclusions. So now we have a new two terms, precision and accuracy. People use these terms in general alternatively all the time without realizing that these are two fundamental terms, fundamentally different terms. So what is precision and what is accuracy? When can we call a data as being precise and when we can call a data as being accurate? Pay attention now. Imagine the dart and arrow game that we play. And we're trying to hit this target here, which is 10. Look, guys, you can use a practical example. Suppose we have a small fiber that we put in it in a scale. That's the digital scale. And we're trying to weigh this fiber. Also, suppose that we know that the weight of the fiber should be 10 ounce. Can you see that? But when we put the fiber on the scale, we get in values such as 5, 6, 6.5, 5.5. So you can see here we have values that are very close, but they are not hitting the target. That's a situation you could easily face with a digital scale, digital balance. Why? Because it's not calibrated well. So as a result, you get in values that are very close, but they are not describing the target value, which is 10. Now, if the values are very close, we call these values precise. So what's precision mean? Precision means values that are very close to each other, regardless whether they actually describe the target value or not, just like this case. So now we have inaccurate data because they are not 10 or even close to 10, but they are precise because the data are very close. The precision describes the closeness of data. Here we have accurate data because they are around the center, but they are far apart. So they are accurate because if you take the average of these black dots, they're going to give you a 10, but they are far apart, so we call this imprecise. Here we have data that are neither accurate nor precise. They are not accurate because they don't describe, they don't hit the center. And they are not precise because they are far apart from each other. And the ideal situation, you can actually guess it now, is data that are very close to the target, that's accuracy, and also very close to each other's, that is precision. So please look at the book chapter and see some examples of accurate versus precise data, because this is one of the questions in the assignment. If not, it will be in the exam later on. Finally, in the definition, we see the two terms, process and system. Many people alternate between these two terms all the time. You write a term paper and then you say the education process or the healthcare process. And in another paragraph, then you change your mind and you say the education system or the healthcare system. Is there a difference between using the term process versus using the term system? Yes, there is, and it's a must know when it comes to statistics to distinguish between process and the system. In your book, you're going to find two good examples of that. When we say process, we mean many different things. We mean people, we mean machine, method, environment, and material. So if I'm talking about the education process, I should be talking about people being teachers or students, environment being a classroom or online as we're doing now, material being books or notes, machine being projectors or computers, methods means face-to-face versus online or e-learning. So process as a term is really a safe term. You can describe anything as being a process because it could mean one or more of these five terms. So if I say education process, I'm in the safe side. No matter where I go, I cannot be wrong because if I'm talking about students as an education process, fine, it is an element of a process. If I'm talking about the methods of teaching, it's a method that's a part of the process. If I talk about machine, if I'm talking about environment, if I'm talking about material. But if I switch to talking about a system, then that's a different story. A system must be defined by inputs, outputs, and perhaps some noise. So anytime you're going to use the term system, you must be prepared to define inputs and outputs. This example here is a machine. a weaving machine, a loom. If we want to call this machine a system, then we have to define the inputs, in this case yards, the output, which is in this case fabric. That is how we define a system. If I'm talking about education as a system, then I must define inputs. The inputs in this case will be the students, the freshman students joining the university. The output will have to be, for example, the graduating students. So when you speak of a system, you must define an input and output of the system. Finally, we need to understand the so-called levels of measurement. I call this the pyramid of levels of measurements. You need to pay attention to what I'm saying here. I'm going to give it to you with a very, very simple example. It starts with qualitative variables, as you can see here, and then it goes all the way from qualitative variables to quantitative variables. The most basic variable is what we call nominal. The top of the pyramid is what we call ratio. As you can see here, going from the bottom to the top, we have to ask ourselves a number of questions. Does the variable simply categorize each individual? Categorization, that means students' names, students' ethnic background. These are qualitative. I mean, if you say that you are white, what does that mean to me? It means an identity. There is no magnitude. There is no order. Being white does not make you twice as much as a black or Hispanic or others. It's just a category. It's qualitative. Then you go to the next level, which is, does the variable categorize and allow ranking of each value of the variable? This is very much like a car race. Yes, if we say the first car that reached the end point, that's the winner, right? But how about the second car? That second car is simply the second car in the race. But that doesn't tell me whether the first car was twice as much faster than the first one. In other words, zero has no numerical meaning here. And meaningful order or ranking can be traced as 1 or 2 or 3 or any. For example, if I have a bunch of male and female in my classroom, in order to look at them, female and male are just categories. Is there a rank there? No. So that takes me back to the first question. These are nominal categories. You follow me? But if I rank students by other means, such as age, such as grades, what's the first students in the class, what's the second students, what's the third students, again, I'm going to mention names of students if I'm allowed to, but that category is now associated with a rank. We call this ordinal. So the bottom one is called numeric or nominal variable. The second one is called ordinal measurement level. The next one here is based on the question is, do differences in values of the variable have meaning? Imagine you are testing your temperature using a thermometer. Here zero has no meaning, because what is zero temperature means? We know it means that the temperature is freezing temperature. Okay, but that's all what we know about. You get my point? So there is an order there, there is a value there is an incremental difference there, but zero has no meaning. So we call this interval measures. Only when zero has a meaning that the variable becomes ratio. Notice that the interval measurement is also quantitative, but the zero has no meaning in it. While the ratios, such as your age, such as your grade, if you get a zero and somebody else get 100, we know there is a big difference between the two. Let me summarize for you the meaning of the levels of measurements in a very simple example. Suppose I am sitting in a restaurant. You follow me? And a waiter or waitress come to me and she's asking me what you like to drink. So my answer is, or maybe she's giving me choices. Would you like hot drink, coffee or tea, or would you like soda, Coke or Pepsi or whatever? Now, my choice being tea or coffee, Pepsi or cola, these are called nominal variables. Why nominal? Because what's the relationship between these? It's just a preference. Me liking tea after I eat or before I eat has nothing to do with somebody else liking soda or juice or whatever. This is nominal. Now, if I choose to drink coffee, so the lady say, okay, sir, we'll get you the coffee. But then she comes back and asks another question. Do you want cold coffee or hot coffee? So now the variable that was nominal a minute ago is being associated with the rank here. Because cold means low temperature, hot means high temperature. So that moved that variable from being nominal to being ordinal. That's the second level. So first, nominal, coffee, tea, soda. Second level is rank, hot or cold coffee. Diet or zero or normal Coke. That is a form of rank here. So it's not just description of the variable, it's associated with meaning of ranking. Okay, guys, as I go from zero to Diet Coke to normal Coke, these are ranks. And that's what we call ordinal variable. Okay, suppose I am in a very sophisticated restaurant and the lady is coming back at me and saying, well, what exactly the temperature of the coffee that you want? We have 60 degrees, we have 70 degrees, we have 80 degrees, we have 100 degrees. I say, oh my God, what kind of question is that? Aha. Now she's taking the variable and converting it from being ordinal into being interval. Why? Because I have numbers now. I have 60, I have 70, I have 80, I have 90, I have 100. So if I choose one of these, I'm really choosing an interval. You follow me, guys? So this lady get me my order, and at the end, she gave me the receipt or the bill. And the value in the receipt could be $20, $50, $100. These are what we call ratio. Because definitely, if my bill is $100 versus the next door guy who's sitting at the next table, if his bill is $50, then I am paying twice as much as this guy is paying, and I'm getting perhaps twice as much amount of food as he is getting. So you really can see now the rank as well as the quantitative meaning, and that is the top of the pyramid I was talking about a minute ago. We go in basic line, nominal, next step ordinal, next step interval, final step is ratio, and I understand some of you will mix between interval and ratio as you will get to do the exercise but I don't think that's a big deal. I will accept it either way. Just use your best judgment. Thank you, guys.